Alrighty. Okay, so let's do a practice problem. I didn't give you a take-home problem. I went soft on you, but take a minute right now and do this practice problem for me. Pause it, do the practice problem. It has to do with everything we talked about last time. So, in this problem, I'm giving you a reaction and I'm telling you that the reaction is first order in A, okay? So I went easy on you. And I'm telling you, and I tell you the half-life and how much you start with, and I ask you how long will it take. Now, if you remember, the key phrase in this question is how long, right? How long is the key phrase. Now, every time we talk about how long, what are you going to do? You're going to use integrated rate law, because integrated rate law is going to relate time and concentration together. So that every time someone asks you how long you need time, you need to look at integrated rate law. Okay, so before I even decide what I'm going to do, I'm going to say, hold on a second. This is how long, which means I need to use integrated rate law. It's a first order reaction. So I'm going to write down all the equations that I know for first order integrated rate law. So I know that R, just say rate equation, is K times A to the power of 1 because it's first order. And because it's first order, the integrated rate law would be ln of A concentration at T over A concentration at the initial equals minus KT. And then the half-life is going to be 0.693 over K. So what these are, basically what I just did, I just put down all the equations I know for a first order reaction. Now I know you probably remember this from last time, but I'm going to mention this because I'm going to make myself feel better about it that I mentioned it. So this one, it means how much A is left. And this one means A at the initial. Alright. Now, first order reaction. These are all the equations I have. I know I have to use the integrated rate law at some point because they're asking me how long. Now, how are we going to do this? They give you half-life. We go, okay, so they give me half-life. So I'm going to use this equation. They give me half-life. So I'm going to use this equation. Because half-life is going to equal 0.693 over K, and I know the half-life is 22 minutes. Okay, so I can do a little math. You guys know algebra. You know it really well. I can figure out what is K from the half-life. Very good so far. Okay, so I have the half-life. So if I have the half-life, this is just a constant. I can figure out K. Now tell me, what will be the unit for K? It will be 1 over minutes. Beautiful. Okay. Now that I know this is good so far. Then I'm going to write down, remember the equation was A going to 2B. Alright, so I have K, which is great. Now I need to use the integrated rate law to figure out how long does it take to produce 0.42 molar of B. Now at T0, at the beginning, how much of A do you have? You have 0.75 molar of A. And at the very beginning, right, when you start, you don't have anything of B. Now then, at T equals T, okay, you are going to have 0.42 molar of B. And the question is how long it's going to take you to get there. You guys are good so far? Now, if you look at the integrated rate law, we're trying to figure out T. Pay attention to this. I have K now. That's great. Now, I have the initial is 0.75, but I also need to know how much is left over at when I have 0.42 molar of B, because this one is all the reactant. What I have is a product. You guys follow that? Okay. Don't worry, at the end I'm going to mention it one more time. So I know I need to use integrated rate law. Here's my integrated rate law for first order. I'm trying to figure out T. I just figured out K. That's great. I have the A initially, but I also need to know how much A is left over to be able to plug it in. Now, how am I going to do this? Well, you know how to do this because you have B. If you have B, can you figure out A? We've talked about this so much. When you have one thing, but you're trying to figure out something else, what do you use? Hashtag mole ratio, right? Every time you have one thing, but you need something else, you can use mole ratio when they give you a balanced equation. So I have give me 1 second. All right, I have 0.42 molar of B that is going to be produced, okay? Now, I don't want the mole of B. What I want is A. What is the mole ratio? Coefficients are the mole ratio. Coefficients are the mole ratio. So for 2B to 1A, so then what I'm going to get is 0.21 molar of A. Okay, now what does that mean? What is that? So that means that I produce 0.42 molar of B. If I do a mole ratio, what does this number represent? This number represents not left, how much was used. Because when you do the mole ratio, you had to use this much to make 0.42 molar of B. You follow me so far? Okay. So when I do the mole ratio, I get how much A is used. That's what I get. But what I want is how much A is left over. Okay, well I know how to do this because I know how much A I started and I know how much A I used. If I subtract it, I can figure out how much A is left over. So what I started with is 0.75. How much was used, was reacted, was 0.21, and 0.45 molar is how much is left over. Okay, you guys are following me so far? All right, beautiful. Now I'm going to go to the next page. Now that I have all the equation and I have everything, I can just plug it in. I can just plug it in. You ready? Let's do this. Let's do this. So we have all the numbers that we need. We have all the numbers that we need. I'm going to have ln. What is A left over? A left over would be 0.54. Initial is 0.75 minus I have the K 0.0315 and T is what I'm trying to figure out. Okay, so when I plug in T, what I end up getting is 10.4 minutes. 10.4 minutes. This was a big one. You guys hopefully follow that. So let me summarize it really quick. I know I took a little time going over this, but if you can understand this, you'll be able to do any problem with integrated rate law. So I'll give you a problem. How long is the key? Because how long means you have to use the integrated rate law. They tell me the reaction is first order. So I'm going to write down everything I know about first order. The rate law, the integrated rate law, and the half-life. I know I have to use this at some point. Now, they'll also give you the half-life. It was like, okay, if they give me the half-life, if I plug it in, I can figure out K. I'm going to do this. I'm going to figure out what K is. Okay, that's great. Now, I know because it's how long, I have to use my integrated rate law. So now I have K. I'm trying to figure out T. Now I have to make sure I have these two pieces of information. I have the concentration of A at the beginning and the concentration of A that is left over at the time that I want. Okay, so I know that 0.75 is the initial. That's great. But I need to figure out how much A is left over at this point when 0.42 molar of B is produced. Now what do? I have B, I don't have A. Mole ratio is my best friend. So I'm going to do a mole ratio, 2 to 1 mole ratio. Coefficients are the mole ratio. So what I can figure out is how much A was used. When I use 0.21 molar of A, 0.42 molar of B is produced. I have how much I started, subtract how much is used, I get how much is left over. Then that's great. That means I have those numbers. I can plug it in and I can get T. Alright, this was a big practice problem. I spent about 10 minutes on it, but that's good. That's good for us. Hopefully you got this integrated rate law down. Ready for next part. Now what we're going to talk about, the next thing we're going to talk about the effect of temperature on reaction rates. So far, we talked about concentration and we talked about concentration and time, right? Now let's talk about temperature. So far we've talked about concentration and reaction rate. We talked about time and concentration. Now let's talk about temperature. I have a question for you. Have you ever baked cookies? Even if you haven't baked cookies, you watch someone bake cookies. So when you bake cookies and it says the oven has to be set to 350, okay? What happens if you go up and then set your oven to 750? Will it bake faster? Or will it just burn? Have you thought about that? Try it out. See what happens. I'm completely kidding about that. Do not do that. Then you're going to end up having no cookies. But that's actually kinetics when you're doing that. You just don't think about it. So let's talk about this kinetics. R is equal K times A concentration to the power of 2. Let me give you a second order reaction. I have 1.00 molar of concentration A. I have at 300 K. Okay. And then I have 1.00 molar concentration A at 350 K. Now, I need you to pay attention to these two. These two have different rate. Why do they have different rate when the concentration of A is not changing? I have 1 molar A, I have 1 molar A, but they are at different temperature. Because they're at a different temperature, they are going to have a different rate. But why? Why would they have a different rate when you plug into the same equation? R is equal to K times the A concentration to the power of 2. Now this A goes over there. This A goes over there. So the concentration is the same. So why would the rate of these two be different? So they have different rate. Why? What do you guys think? So A and B have different rate. The question is why? When they have exactly the same concentration. The concentration A is not changing and you just plug it in this in. The reason is because K is temperature dependent. These two reactions, these two experiments are going to have different K. Because K, it must be temperature dependent. So K is temperature dependent, is T dependent. And I need you to remember that. So this is why some people go, well, if they have the same concentration, so the rate is going to be the same. It's like, no, because the K is going to be different because K is temperature dependent. So far, so good? Okay. Now, you'll kind of notice, but I'm going to write it anyway. when you increase the temperature of a reaction, what happens to the rate? The rate goes up, right? And you kind of notice from high school chemistry or just cooking that the rate goes up when you increase the temperature. Okay? Now the question is, what happens? Why does the speed goes up? Why does it happen faster when you increase temperature? Why is that? So that's what we're going to talk about right now. Why is that? Now, a little reminder from Chem 1A. You probably don't want to hear that. You're going to block those days out. So, do you remember about the speed of gas molecules? Or the velocity, which is a fancy way of saying speed. If you remember, the equation was 3RT over molecular weight. Yeah? And what that equation meant was that if a temperature goes up, the speed is going to go up, right? If a temperature goes up, the speed is going to go up. And why is that? When the temperature goes up, the molecules move faster. The molecules move faster. So hopefully you remember that from Chem 1A. Now let's build up on that a little bit. Let's say I have this reaction. AB plus C goes to AC plus B. Okay? Now, do you agree that the first thing that happened is that AB needs to collide with C? Okay? So, the first thing that happens, and let me rewrite this again, that AB, they need to collide. They need to collide with C. Yeah? Now, it doesn't matter how it collides. It does matter. It's not just, they collide, they're going to react. The orientation matters. They have to collide at the right orientation. Okay? So, what matters is orientation matters. Because it has to collide at the right angle in order to break a bond. So far, so good? Okay. Now, the second one is that to break a bond, do you agree that is going to cost energy, right? So, energy matters. So, energy matters. Because what's going to happen is this bond is going to be broken. So when this collision happen, it matters that it has to happen at the right orientation. The orientation matters. And also, to break a bond, it costs energy. I need you to remember that. To break a bond is going to cost you energy. So energy matters. So far, so good. So for this reaction to go, orientation matters and energy matters. Now, this is what happens when you raise temperature. This is what happens when you raise temperature. Two things happen. When you raise temperature, the molecules move faster. The second thing that happens, when you raise energy, when you raise temperature, temperature is energy. Temperature is energy. Remember that. Temperature is a form of energy, right? Heat is a form of energy. You have more energy to break bonds. That's interesting. So, let's take a step back to make sure you really understand this. This is my reaction going on. I have A, B, and C. They need to collide in order for this reaction to happen. Well, orientation matters. They have to collide at the right angle, otherwise this is not going to happen. Also, when you collide, you need enough energy to break this bond because it costs energy to break a bond. Okay? I usually use this bad example that if you're trying to break up a couple, you need to put some thought into it, right? You need to put in energy to do that. Bad example though. Okay, so you need these two things in order for reaction to happen. Well, when you raise the temperature, the molecules move faster. When you raise the temperature, the molecules move faster. I just showed you over here. When you raise the temperature, the velocity goes up. The molecules move faster. Now, when the molecules move faster, what that means is they are going to have more collision. Because if you're moving around faster, you have a higher chance of colliding to things. Do you agree? Now, because you're having more collision, there's going to be a higher chance of getting the right orientation. Did you follow that? Hopefully you're saying yes. I'm going to repeat it one more time. So you raise the temperature. The molecules are going to move around faster. I just showed you this. Temperature goes up, the speed goes up. When the molecules are moving around faster, what that means is you're going to have more collision. Because if you move around faster, you have a higher chance of colliding into things. Now, the more you collide, the higher number of collision that you have, that means you're going to have a higher chance of getting or colliding with the colliding at the right angle, at the right orientation. That means I'm talking too much and I can't talk anymore. Yeah? So more collision means you have a higher chance of getting into the right orientation. Perfect. Now the other thing is, so that's taken care of when you raise the temperature. That energy matters. So now when you increase the temperature, that means you're going to have more energy to break bonds because heat is a form of energy. Heat is a form of energy. So now you're going to have more energy to break the bonds. So these two requirements are going to be met when you raise the temperature. All right, so far so good. Hopefully you got this down. Now I'm going to put up this graph. So remember, this is our equation, A, B, and C. This bond has to be broken, and then I'm going to form the AC, and then B is going to be by itself, single replacement reaction. Lots of drama going on there, but no judgment. Now let's come over here. So I'm going to put it in a graph for you. So I have A, B, and C. C is going to break up this bond, and I'm going to have, AC, and I'm going to have AC plus B. So far so good? Okay. Now, what this means is that there's an energy barrier. You need this much energy to be able to break the bond. This is a barrier to be able to break the bond. Now, I want to give you a non-chemistry example to make more sense. Let's say I have a ball right here. If you want the ball to go over the hump, you have to hit the ball with enough energy. If you don't hit the ball with enough energy, it's not going to go over the hump. It's not going to go over the barrier. It's the same thing. I need enough energy to get over this barrier. I need this much energy to be able to break the bond. So far so good? Okay. Now, so again, let me summarize this. There's a minimum energy I need to be able to break the bond, which brings us finally to our equation, and that is activation energy. Activation energy. What's the activation energy? Here's what activation energy is. You ready? Activation energy is the minimum energy required for a reaction to happen. You were probably wondering what I was going with all those examples. So now you know. Activation energy, the minimum energy required for a reaction to happen. Because you're going to remember for me that it takes energy to break a bond. You can't just break a bond. You need to put in energy to break a bond. Okay? And again, that's exactly why we need a minimum energy. So we need a minimum energy because, first of all, you have to break the bonds. And second of all, when you need molecules to move fast, because once they move fast, they're going to collide. And when they collide, you have more chance of getting it at the right orientation for the reaction to happen. All right, now let me put in a crazy equation. K is equal A times E to the power of minus activation energy over RT. This is our equation. Okay. K is the rate constant. You know that one. A is a frequency factor. Now, when we go on top, EA, that just means activation energy. That's activation energy. And I should have not circled the whole thing. Let me see. Let me do a better job of circling this. Okay. I didn't want to circle the minus because EA is activation energy. Okay. Now, R is a constant. The R constant you had in Chem 1A, 8.314, which is joules over Kelvin times mole, which means temperature has to be in Kelvin. All right, this is our activation energy. Sounds good? I actually want to stop right here because I talk too much today. So this is our equation. This is the activation energy. We need a minimum energy is required for a reaction to happen. Why? Because you need energy to break the bonds, and also you need energy so they could collide at the right orientation in order for reactions to happen. Yeah? All right. So nice job today. And next time we will do some practice problem with activation energy. I'll talk to you guys next time.